Alright, hello everyone. Today we're going to be looking at some physical properties and trends of organic molecules. Alright, let's get into it. We're going to start with a little recap of some intermolecular forces that you might find in organic molecules. So you have intramolecular and you also have intermolecular forces. So the differences between them: intra, right, that means within the molecule. Okay, and that's when you're talking about your covalent bonds. Alright, so that's covalent bonding. And that's when those same atoms within the same molecule share one or more electrons. Okay, so it's covalent bonding. That's intra. And you also have intermolecular. So intermolecular forces, what they are is forces between different molecules. So intermolecular, alright, forces between other molecules. So that's going to be things like dispersion forces, and things also like your dipole reactions between molecules. So that's when there's a definite positive or a negative charge on one side of the molecule, and it reacts with another charged area of another molecule. So dipole interactions. Now I'm going to put hydrogen bonding here because it happens both intramolecular and intermolecular. So I'm going to put it in both. What hydrogen bonding is it can be a type of covalent bond, but it's when hydrogen bonds with oxygen, fluorine, or nitrogen. Okay, so that's hydrogen bonding, and it can also cause intermolecular forces as well. Alright, so that's our intra and intermolecular forces. Alright, you don't have to worry too much about what category they fall under, because often they'll overlap. Like with our hydrogen bonding can occur or does occur within a molecule, but it can also occur outside between two different molecules, which is what we see in protein chains. Which we'll talk about a little bit later. Hydrogen bonding and dispersion forces, they all occur within the molecule itself, but they can be responsible for intra and intermolecular interactions between different molecules. Alright, so let's talk a little bit more about what each of these different forces mean. Okay, so what have I drawn here? This is obviously propane. The reason for that, we have 3 carbons and we just have single bonds to hydrogen. Okay, so that gives us propane. Now we're going to talk about the different forces that are going on in between this molecule here. So first off, we have covalent bonding between these carbon atoms. So carbon to carbon bonds and also carbon to hydrogen bonds. They're all examples of covalent bonding. That's basically the bonding that occurs when we keep those atoms together. So all of these lines here, they represent a covalent bond between two different atoms. So between the carbon and the hydrogen atom here, there is a covalent bond, which is an intramolecular force. Okay, and what you'll also find is you'll have dispersion forces. Now dispersion forces, what they are force electrons that move around the carbon chain. So electrons are moving all around this molecule here. So and at any specific time, you might have more electrons on this side of the molecule than you do over here. So what this will create is a temporary dipole. Okay, this is very limited, like it obviously doesn't happen all the time. But what you'll find is if you have enough atoms and enough electrons in the molecule, then those temporary dipoles will happen more often. So dispersion forces, they increase when you have a longer carbon chain or a bigger organic molecule. It also influences other things such as melting point, and also solubility as well. So back to propane. Propane is a relatively small carbon chain. Right, when you have 3 carbons in the chain, if we compare that to something like pentane or butane, they obviously have more carbons in the chain, and that is going to actually increase the atom's melting point and boiling point. So a molecule like this, we have propane. It's going to have a relatively small boiling point or melting point when we compare that with something like butane, not necessarily butane, because that's only one more carbon, but something like hexane or septane, where we have 7 or 6 carbons in the carbon chain. This is going to have a lower melting and a lower boiling point when we compare with those other molecules. Okay, so what I've written here, melting and boiling point, some things that affect that is the carbon chain length. So increase boiling point and melting point when we have a longer carbon chain. Alright. Now there's also some other things that can affect melting and boiling point of molecules. Alright, so what we've got here is a slightly different molecule. Okay. Got the same number of carbons, but the functional group has changed. Alright, it's no longer propane, but instead we have a carboxylic function group on the end, carboxylic acid. So it's actually now propanoic acid. Alright, so what does this mean in terms of melting and boiling point of the molecule? So because this functional group's changed, we now have a oxygen bonded to this carbon, double bond to the carbon, and we also have a OH group bonded to the carbon here, is because we have a hydrogen bond here. So we have a hydrogen bond on that last molecule. That indicates that it's going to be harder to separate. So the hydrogen bond means that if the bond is harder to pull apart, it requires more energy for that oxygen and that hydrogen to separate. So because it requires more energy, it requires more heat, therefore the melting point or the boiling point of the molecule is going to be higher because it requires more energy to separate those bonds. Alright, so because we have a hydrogen bond and a double bonded oxygen here, they require more energy to separate from the molecule, and therefore they're going to have a higher boiling point and a higher melting point. Okay. So another thing that can impact this is the functional group. And one thing you should also know is that when we have a molecule like this one here, this is a carboxylic acid, but if it was an alcohol, so if we switched it up, we have an alcohol, so we've got that OH group there attached to the last carbon, so this is now propanol. A alcohol typically has a lower melting and boiling point than a carboxylic acid, but a higher melting or boiling point than a alkane, alkene, alkyne. Okay, so the reason for that is because of the functional group and those intermolecular forces. Okay, so what I've just written there, the carboxylic acid will typically have the highest boiling point, the highest melting point, and then it will be an alcohol, and then alkane, alkene. Alright, that's just because of the intermolecular forces. Alright, so that's melting point and boiling point. Now we're going to talk about solubility a little bit more. Alright, now let's talk about solubility a little bit. Solubility basically means how easy does a organic molecule dissolve in water. Okay, so for instance, if we had a long carbon chain organic molecule, something like pentane, hexane, septane, if we put that in water, it's going to be harder for that molecule to dissolve because of its increased carbon chain length. So if we have 6, 7 or 8 carbons in the carbon chain, it's actually going to be harder for that molecule to dissolve in the water when compared to something like this here. Okay, so solubility in water, general rule of thumb, this is the longer the carbon chain, the less soluble that molecule is in water. Okay, so I'll write that down. Okay, so what I've written there, increased carbon chain length equals a less soluble molecule. Okay, one thing that will also influence its solubility is again that functional group on the molecule. Okay, so the functional group now the reason why the functional group can affect solubility is the ability of those alcohol functional groups and carboxylic acid groups to form hydrogen bonds with water molecules in solution. So alcohols and carboxylic acids are more soluble in water than alkanes, alkenes, and alkynes. So general rule of thumb again is similar to this here, right? So carboxylic acids and alcohols, they are both more soluble in water than alkanes, alkenes, and also alkynes as well. Alright? So any hydrocarbon is significantly less soluble in water than a molecule that has that hydrogen bond in it. Okay. Alright. So that's some things that determine solubility is the carbon chain length and also the functional group. Okay, so I also want to talk a little bit more about volatility and what that means. So it is related to boiling point, but it's kind of opposite. So what I mean by that is if we increase the boiling point of a molecule, that means it has a lower volatility. So if we take water, for example, that has a boiling point of 100 degrees Celsius, that's actually going to be a low degree of volatility when we compare that with something like propane or butane, which has a much higher tendency to vaporize than water does. So it's the tendency of a molecule to vaporize. So if a molecule had a high volatility, it would mean it has a very low boiling point. Okay. So if we link it back to what we were talking about before, if we have a increased carbon chain length, that is going to decrease the volatility because it makes it harder for that molecule to boil. Alright, so if we have a carboxylic acid, that is generally going to have a lower volatility than an alkane or an alkene. So we've talked about solubility a little bit. We also need to talk about solubility in water and organic solvents. So this rule here, this is true for water. So this is when we put a organic molecule in water. Okay, but we also need to understand what happens when we put a molecule in an organic solvent. Alright, so if we put a carboxylic acid in an organic solvent, it's actually going to be less soluble than an alkane and an alkene. So what happens in an organic solvent is it kind of flips around. So increased carbon chain equals more soluble. This is for organic solvents. Alright, and alkanes alkenes. They are the most soluble. Right. This here is for organic. Organic solvents. Okay. So the reason why this happens, the reason why it's true, non-polar molecules dissolve non-polar molecules and polar molecules dissolve polar molecules. So for this one here, we have a non-polar molecule, an organic solvent, and alkanes and alkenes are typically non-polar or less polar than a carboxylic acid or an alcohol. Okay, so they dissolve more than those other two functional groups. Alright, so that's pretty much everything for physical properties and trends. This is everything that is covered in the syllabus. So if you understand this and kind of the theory behind it with those forces, so those hydrogen bonding and dispersion forces that we talked about at the start, then you will be in a good place for your exams. Thanks.